So what happened after you did everything? And so your final answer, folks, if you did do it with your buddy, okay. I'll put it mine in component form just because I prefer that. My first component ended up being 3y squared z squared minus 1. Does that look like what you guys got?
Yeah.
Yeah.
Yes.
Think so?
Yeah.
Okay. And then the second component, after cleaning it up, ended up being positive 4xy squared z cubed.
That's right.
Mm-hmm. And then the last component was 4xy minus 2xyz to the fourth power. Woo! Did you guys get that?
Splendid.
Yeah, actually. Somehow.
Yeah.
Oh my God. Okay, so that is the curl. And please note that this curl is itself a vector field. That's important for you to understand. The curl of a vector field is another vector field, essentially. You get a vector field result. So is this the original vector field? Is it conservative or not? Yes or no?
No.
No.
No, it is not, because you get
Whoa.
the zero vector. If you had gotten the zero vector for curl, then it would have been conservative. So yeah, so this question is curl a vector field or a scalar function. It is a vector
Vector
field.
field.
Just know that. Now, here's a little extra for you. Curl involves the cross product. And you guys know from like the beginning of the semester, cross product is only meaningful on three-dimensional vectors. You can't do a cross product of, you know, a couple of vectors in two dimensions. Doesn't make sense. So what if you were asked to find the curl of a 2D vector field?
Mm.
And there actually is something, but different books kind of call it a different thing. So one thing that some folks do is they take the two-dimensional vector field and they embed it in 3D. So they make it like, well, okay, we're gonna embed it in a 3D system. But then that means that the P component is zeroed out. So then when they do this cross product thing, you know, that whole shebang, they end up with you know, negative dn dz, dm dz, and dn, dn, I can't write. I'm really blowing this. And the reason why I have some of these is because this guy's zero. So you get some things that are zero. And then this last guy ends up being dn dx minus dm dy. But m and n are functions of x and y. So if you were asked to take the partial of m or n with respect to z, guess what? Those are just going to be zero. But this last component is not going to be zero, okay? Unless it's conservative, of course. You know, dn dx equals dm dy. So then what? So a lot of times, and this is what Briggs does, Briggs says this right here is your curl of your 2D vector field, which is a little bit cheesy because curl is supposed to be a vector field, okay, not the, you know, a component of a vector field. So other textbooks argue the following. They argue that they're going to take this curl of f, which is a vector field, and if you dot product the curl of f with k hat, which is the vector 0, 0, 1, then you get the dn dx minus dm dy, which is a little bit more spot on, if you will. So the reason why I'm getting into this, like, who cares? And there's my meme. You know, when you're doing greens, so let's just look at greens again. The circulation form of greens, now that you know there's two versions. So if I look at the circulation form of greens, and this is important that you get this. You're going to be good little vector calculus students. Some books will replace this thing right here with this. So you may see greens written like this. It's written in a vector format, this two-dimensional or this double integral. So instead of dn dx minus dm dy, some textbooks will go, well, that's the curl of f dot product with k hat ea. Same thing. Those are both equivalent. So I just wanted you to see that so you don't freak out if you look at other textbooks and they talk about greens looking like that. Because the circulation, this is a circulation integral here, circulation integral. If you're figuring out circulation, circulation basically corresponds to curl. And we're going to see the 3D version of this when we look at divergence theorem. Okay, so I'm done with curl. Let's do divergence. You gotta learn both in this section, divergence and curl. Divergence is easier than curl. I wanted to do the hard one first. So good news, this is easy. So what is the divergence of a vector field? It's easy. For a 2D vector field, you take that hollow differential operator, the one that's just ddx, ddy, because it's 2D, and you take the dot product of it with the vector field. So basically this kind of looks like, if I do this in slow motion, you're taking this hollow differential operator and you're doing the dot product with the vector field. So then when you do the dot product, you go, oh, I'll take dm dx plus dn dy. And that's known as the divergence of your vector field. And then you do the same thing for a 3D and you get the divergence of a 3D vector field. So it's really easy to find because it involves the dot product, not the cross product. So now let's talk about a really nice mnemonic for you. You notice how curl of f involves the letter C? Well, the word cross in the phrase cross product involves the letter C. And then when you're taking the divergence of f, it needs the dot product, and the word divergence starts with the letter D, and the phrase dot product begins with the letter D. Is that helpful?
Yeah.
There you go. You're welcome. So the dot product notation we just discussed. So let's get some divergence here. So the divergence of this vector field here, and then we'll evaluate it at a point. Okay, fine. So that'll be kind of fun. So the divergence of f, which is denoted like this with this differential operator, is going to be simply, we're going to take the partial with respect to x of the first component plus the partial with respect to y of the second component plus the partial with respect to z of the last component, and add them all together. Easy. So I think this one's going to be 3x squared y squared z. This one's going to be 0. Nice. That one's going to be 0. That's even better. Great. So all we get is the divergence is 3x squared y squared z. Fine. So then what is the divergence of f evaluated at the point 2, 1, negative 1? Well, you just substitute. So you're just going to have 3 times 2 squared times 1 squared times negative 1. And I get negative 12. And there's your answer. So what the heck is divergence and who cares about it? Like, what does it have to do with real world? So it's a type of derivative that represents velocities of moving particles. Really? Yeah. And what it does is it measures the rate of particle flow per unit volume at a point. So what? Where's my other? Yeah. So it's basically measuring, how much flow at a point is happening. Like if you've got a lot of flow happening, a lot of particles moving through a point, you're going to have a high divergence. It'll be positive. Is it going in the opposite direction? It'll be negative. If it's 0, well, it's divergence free. Okay, so they call that incompressible. Why does it always do this? If it's divergence free. So that's some vocabulary for you. I don't know what my PDF is doing right now. Okay, now, if you're studying electricity and magnetism, and there's a lot of vector fields in that, magnetic fields, electric fields, a vector field that is divergence free has a special name. It's called solenoidal. Interesting. Emily, no, this has nothing to do with divergence and convergence of sequences and series. But nice try. Yeah. Sorry to disappoint. Yeah, this divergence, like, hey, I did Calc 2 and we discussed divergence of a power series that, no, got nothing to do with that.
I like this kind of divergence.
This is a different, totally different divergence. This is more like flow of particles. Yeah, but that's got nothing to do with a divergent series. I know, sorry. But they use the same word, darn it.
Thank God it has nothing to do with it.
What's that?
Thank God it has nothing to do with it. More like.
Mm-hmm. Mm-hmm. Well, it's like, here, I'll give you some food for thought. A chickpea is neither a chick nor a pea. Discuss. Sorry, I digress. I like that other one that Mike Myers does. Rhode Island is neither a road nor an island. Discuss.
Coward thoughts.
There are roads on Rhode Island.
Okay. There's many important properties of divergence and curl. Okay. Go take a physics class if you want to get the full Monty there. Okay. So let's do the theorem for divergence and curl. Do these two things have any relationship to each other? Like, is divergence related to curl, or is curl related to divergence, or do they have nothing to do with each other? Well, there is some relationship. Check it out. There's two biggie theorems that I want you to keep your eyes on. One of them is the following. So this is biggie. I'm going to call this biggie theorem number one. That's a technical term, biggie theorem. Yeah. Okay, so if you've got a nice vector field, let's say the components are M, N, and P, and of course Briggs sucks, so Briggs is probably going to say F, G, and H. Yeah, Faraday's law might work with it. Yeah, it's a vector field, and M, N, and P have continuous second partial derivatives. Then if you take the divergence of the curl of F, it'll end up being 0. Okay, so that's a nice biggie theorem. I'm going to prove this for you. One time I put this proof on a final exam and one guy got it, okay, which was kind of cool. So here's the proof. If you look at the curl of F first, like look what's inside parentheses. If you use the theorem after you do the curl, you have dp dy minus dn dz. And then the second component is the opposite of dp dx minus dm dz. And then the last component is dn dx minus dm dy. Okay, fine. Then somebody goes, well, I want you to take the divergence of that thing. Now remember, divergence, you take the partial of the first component with respect to x plus the partial of the second component with respect to y plus the partial of the last component with respect to z. So I'm going to write all that crap out. So take the partial with respect to x of the first guy plus the partial with respect to y of the second guy. Okay, and then plus the partial with respect to z of the very last component. Fine. Now what you're going to get is a whole, not the angular brackets, what am I doing? You're going to get a lot of second partials, because when you take a partial of a partial, you get a second partial, right? So using some of the weird notation of second partials in differential form, like if you distribute this partial with respect to x, the first thing you'll get is d squared p over dx dy, and then you'll get d squared n over dx dz, plus, and then I'm going to distribute the negative at the same time I distribute the d dy. So I'm going to get minus d squared p over dy dx, and then minus d squared, or is that a minus minus? I'm sorry, that's going to be a minus minus. So it's going to be d squared m over dy dz, and then plus, and then I'll distribute the d dz. I'll get d squared n over dz dx minus d squared m over dz dy. Now, What do you guys know about the mixed partials? Remember that equality of mixed partials theorem from like 2 months ago? Say yes.
Yes.
Good. You're going to use that because some crap is going to cancel. Really? Yeah. This d squared p dx dy is basically the same as d squared p over dy dx, and you got a minus there. Goodbye. And then minus d squared n over dx dz, you add it to d squared n dz dx. Goodbye. This guy and this guy, mixed partials, cancel. Big fat zero, boom, I'm done with proof. Okay? That's
Whoa.
why mixed partials are equal. Okay? It all goes away. So the second biggie theorem on how curl and divergence are related to each other is the fact that if you take the curl of a gradient, that's the gradient, you will get the zero vector, okay, where this phi is a scalar function, which is kind of cool. That's a nice biggie. I'm not going to prove it, but you would also prove it using second partial equality. All right, now if you're cool, you bought this T-shirt already. By the way, this T-shirt I believe does exist. I don't own one, but if you want to impress your friends, you could go get this. So you know, some physics stuff for you. So the divergence of curl, the divergence of the curl. That's one of the biggie theorems that we just did, right there. Okay, so nice T-shirt, kid.
I do have
Okay.
a meme that relates to that shirt. I'll have to send it to you.
You have the shirt out?
Yeah, it's not these, it's more basic integrals, but it's like during an exam, a kid's wearing a hoodie printed with like every known basic integral on it for the students behind him. I'll have to send it.
So in other words, they weren't allowed to bring a cheat sheet in, but they didn't say anything about bringing in a cheat sheet hoodie.
Exactly.
I love it.
Sitting in the front, then it wouldn't work.
Yeah, if you're sitting in the front, too bad. You got to sit behind the guy. Okay. So let's finish today's lecture with meaningful yes or no. Okay. Now, if you get that one of these things is meaningful, then you have to say if it's a scalar function or a vector field. So keep in mind, I just taught you divergence and curl. Curl is a vector. When you take a curl of something, you get a vector. When you take a divergence of something, what do you get? This ain't no vector. Not a vector.
Scalar.
It's a scalar function. A scalar function is the result of a divergence of a vector field. Okay, so knowing that, let's have some fun with divergence, gradient, and curl, div, grad, and curl. Okay, is the curl of f equal to the cross product of the differential operator with the vector field? Meaningful or not?
It's meaningful.
Yes, it's meaningful. This is good. And what do you get? Well, this is the definition of curl. You get a vector. What about this? The gradient of f is equal to del f. Yeah, that's meaningful.
Notation.
Yeah, this is just different notation, but it's totally meaningful, and you also get a vector. Grad of f means the same as del f. This is good, okay? How about divergence of f is equal to the dot product of the differential operator with a vector field? Yeah, that's the definition. We're good. And you get a scalar function. Okay, now it's going to get weird. Are you allowed to take the curl of a gradient, or is that complete BS? And if I use the del operator notation, it would be written as when you're taking curl, you take the cross product of a gradient. Is that legal? And the answer is, yeah, it's good. You're allowed to take the curl of a vector field, essentially. And what are you going to get? A vector, another vector field, actually. Actually, you're going to get the zero vector because of the Biggie theorem. Biggie theorem. Okay, what about the gradient of a vector field? No, that is meaningless crap. You can't do that. Because when you take a gradient, you're taking a gradient of a scalar function. So this is like meaningless dribble. Okay, move on. Letter F, can you take the gradient of the divergence of f, where f is a vector field? So the notation would be del operator del dot product f.
Divergence is a
Yeah.
scalar, right?
You can take that.
Yes, yeah, this is totally good.
It's just
You're
a
just-
scalar
you're
multiplied
just
by another
saying-
scalar.
Well, you're taking the gradient, this is the gradient of a scalar function like this, and you will get a vector. Okay, how about, are you allowed to take the divergence of a gradient of f, which the notation would look like del dot product del f? And the answer is, yeah, that's good. And you're basically saying, what's the divergence of this vector field? A gradient is just a very special vector field, and you would get a scalar. How about the gradient of the divergence of a scalar function? Well, this right here is meaningless. You can't take the divergence of a scalar function. Divergence, by its very definition, you're only allowed to take the divergence of a vector field. So this is crap. Okay, keep going. How about curl of a curl? Can you take curl of a curl?
Sure.
Yeah, you can. So look at the guy's t-shirt had curl of a curl. See? You guys' t-shirt there? That's totally cool. Yeah, you're allowed to take curl of a curl, and you're going to get a vector field. So this is good. You'll get a vector. Curl of a curl, totally legal, totally legit. Okay, how about divergence of a divergence? Meaningless crap. Well, how come? Because this right here, the stuff inside parentheses is a scalar function, and you can't take the divergence of a scalar function. You're only allowed to take divergence of a vector field by its definition. So this is meaningless crap. How about letter K? Can you take the cross product of the gradient of f, and you know gradient of f is a vector. Can you take the cross product of that vector with the divergence of a vector field?
It's meaningless.
Yeah, that's meaningless. Because this right here is a scalar function, and you guys know from your knowledge of cross products, you can only take the cross product of a vector with a vector. You can't take the cross product of a vector with a scalar function. That's like, you can't do it. Okay, now this one's really weird. Can you take the divergence of the curl of the gradient of f?
Yeah.
Yeah, you can. That's totally okay. In fact, you're going to get the number 0. Because the curl of a gradient is going to be the 0 vector, because the gradient is conservative. You take the divergence of the 0 vector, well, you'll just get 0. So cool beans. All right, and we're completely done with
Oh,
a
wow.
divergence and curl. And you may, if you're really into physics,
Brutal.
this is some physics stuff.
That's
for ya.
hardcore.
That's really hardcore tattoo there. I think this is real. Like, I pulled this off the net. Like, wow, that's intense.
You better get that
yeah.
updated like every 20 years. That
It's all magnetism stuff. I think some of that was
With that
definitely
guy in the
fair.
bar.
Yeah, well, the B, I think, is a solenoidal field and some other
Yeah,
stuff.
B stands for the magnitude of the magnetic field as defined by a solenoid, and the fuck. I almost cursed. This is all
almost
Faraday's
you
law
just
stuff.
did.
This is all
Yeah,
Faraday stuff.
too
This is all
late.
Faraday stuff.
Yeah.
That's the point.
All right. Well, so do you have one of these tattoos, David?
He has an
Um,
entire sleeve.
Yeah. You know what? Like, to pass the class, like, you have to just coat your like walls and formulas at this point. Not gonna lie.
You got to get one of those cheat sheet hoodies.
I have to get a cheat sheet house. Like.
All right,
every
guys,
inch.
I'm essentially done with today's dazzling lecture, and I hope you all have a great weekend.